Okay, so in this last section of Chapter 3 of the lecture notes, Chapter 2 of the class textbook, we're going to talk about bumper cars, or really just any set of colliding objects. Cars, people, billiards, whatever. You know, the questions we want to start asking in this section are like, why is it that when a stationary object gets hit by a moving object, the stationary object starts moving? When two cars crash together, what aspects of the motion of those objects are actually transferred between those cars, and why? You know, what governs the behavior, say, of billiard balls as they bounce off of each other? To answer all of these questions, in this section, we're really going to start thinking about two more conserved quantities of motion: linear momentum and angular momentum. Okay, so let's start with linear momentum. And I'll often just write this as momentum when, from the context, it's clear that I mean the momentum, the quantity which is associated with objects translating through space, their center of mass motion, rather than their rotation. Okay, so how do I want to start this discussion? You know, we already learned about energy and how it's a conserved quantity. So when two objects collide, they typically exchange some of this scalar quantity, energy. You know, maybe they trade some kinetic energy back and forth. Maybe they deform each other a little bit or heat each other up or something like this. And they do this all in such a way that the total energy before a collision is the same as the total energy after a collision. Okay. And the important thing about energy is that it's a scalar quantity, right? It's just a number and a set of units. There's no direction to it. But we know from our daily experiences that there's something directional about how collisions work, right? If you're sitting at a red light and you get rear-ended, your car doesn't suddenly lurch backwards or to the left or to the right. It lurches in the direction that it was just hit, right? So there's something directional about how collisions work, and it turns out there's a conserved quantity associated with that directionality. And that conserved quantity is called the linear momentum, okay? So the linear momentum, which we'll write as a vector p, vector lowercase p, is something that we already have something of an intuition for. So this is going to be a conserved quantity associated with the translational motion and direction of moving objects. We already have a sense of things like, you know, it's harder to stop a car moving at 10 miles an hour than like a person on a bicycle moving at 10 miles an hour. It's also harder to stop a person on a bicycle moving 40 miles an hour than one 10 miles an hour. So there has to be, we intuit, some sense in which the momentum of an object depends both on the mass of that object and its velocity. And it turns out the momentum is defined as the simplest possible combination of those two things. The momentum of an object is just the mass of that object times its velocity. So you'll notice, momentum is a vector quantity. It points in exactly the same direction as the velocity of an object does. And the magnitude of momentum is just the mass of the object times the magnitude of the velocity. So that kind of combination has all of the features that we just kind of intuitively talked about. More massive things have more momentum, faster moving things have more momentum, and the direction of momentum is in the direction of velocity. Right. So when I say that momentum is conserved, that means, like energy, it's something that you can't create or destroy. You can only transfer it back and forth between different things. So here's a classic kind of intro physics puzzle. For whatever reason, I've been trapped standing at the center of a frozen lake. And the ice on this lake is so slippery that I can't move. So it's one of those fictitious frictionless surfaces where if I try to take a step forward, because there's no traction, I'll just fall flat on my face. So, you know, here I am sitting with my hat. In the textbook, it's a shoe, but I can't draw a shoe, so it's a hat. And, you know, the question is like, how do I escape? I can't walk, because if I walk, I'm just going to fall down, and I'm not, you know, close enough to solid ground that I can get a traction on, that I can just move away. So what do I do to get around this scenario, escape the frozen lake, and make it to shore? And what you do is you think about the fact that momentum is conserved, and you decide to throw your hat, or I decide to throw my hat. So I don't know why I'm drawing it over there. So I do some work. I send the hat flying off with some velocity of the hat, and what I discover is that I start drifting off with a velocity in the opposite direction. Why does that happen? Why does this strategy work in this frictionless environment? It's because linear momentum is conserved. So what's the linear momentum of the total system that I'm thinking about in this initial scenario? Well, the momentum of every piece of this scene is just its mass times its velocity, and nothing is moving. So the total momentum here p total, is in fact 0. And since momentum is conserved, that means no matter what I do, the total momentum of the system is going to be 0. So down here, after I've thrown my hat away, I have p total being equal to whatever the momentum of the hat is, plus whatever the momentum of, let's say, the person is. That's given by the mass of the hat times the velocity of the hat, plus the mass of the person times the velocity of the person. And this is all equal to 0 by conservation of momentum. So I can just rearrange this equation then and discover that after I throw my hat, and that's easy enough to do, after I throw my hat, I discover that my velocity is equal to negative the ratio of the mass of the hat to the mass of the person times the velocity of the hat. So indeed, I end up moving in the opposite direction that the hat starts moving, and the ratio of the speeds is based on the ratio of these masses. So if I could have thrown a heavier hat, I would have made it to the shore quicker. Or if I threw the hat faster in the first place, I would have made it to the shore quicker. Okay, so that's great. So we have this quantity, linear momentum, which is a conserved vectorial quantity, which is a property of the motions of the center of masses of objects as they go through the world. Another very similar conserved quantity is angular momentum, right? So just as there's a momentum associated with objects moving at some velocity, there's an angular momentum associated with objects rotating at some particular angular speed. And we've already done all of this work to set up our language of rotations so that the laws of motion look and feel the same when we're talking about rotations and translations. So I hope that you can actually already guess what the equation for the angular momentum of an object is, right? Just as linear momentum, p, vector, is a vector quantity that points in the direction of a velocity, and it's given by the mass of an object times the velocity of that object, the angular momentum, and we'll use the symbol L with a vector, is a vector quantity, and it's given by the product of the angular mass, which we've also called the moment of inertia, this letter I, multiplied by the angular velocity. So it's a momentum, which is a type of mass, times a type of velocity. So it's another conserved quantity too, just like energy and just like linear momentum. And this thing is associated not with objects translating through space, but with objects spinning about some pivot point, usually the center of mass, but if you have a fixed pivot point, it can be something other than the center of mass. Okay, so again, just like the regular linear momentum, there's a direction associated with angular momentum, and it's the same direction that the angular velocity is pointed in. And remember that vector quantity, we use the right-hand rule. So if I have an object like this pen that's spinning this way, maybe that's hard for you to see, so I'll replace it with this coaster that's spinning this way. So I curl my fingers in the direction of rotation, and my thumb is pointing, in this case, up. That's the direction associated with both the angular velocity vector and the angular momentum vector. Now, a classic illustration of an example of conserving angular momentum is one that relies on the fact that angular mass is something that depends, remember, on both the total mass of an object and the way that mass is arranged, and how the mass is arranged. Sorry for the lag as I write there. Right? And we haven't written down any formulas for how you determine this moment of inertia, this angular version of mass, but one thing that you can realize, or one thing that I can tell you, is that, for instance, if I stick my arms out and try to rotate, having my arms out, having mass away from the axis about which I'm rotating, is a way of distributing mass to get a bigger moment of inertia. And if I bring my arms in, and I'm going to spin about, a line going up and down right through me, that's a way of changing the positions of the mass associated with me in such a way to lower my moment of inertia. Okay. So how is it then that figure skaters can perform very fast spins on ice? At first, they start rotating, they exert forces, and we'll talk about giving yourself impulses in just a moment. They start out spinning with their limbs extended, and that gives them a big moment of inertia, a big angular mass. And they then set themselves up in a spinning state, and they have a certain amount of angular momentum. Angular momentum is conserved, so then when they bring their arms close to their center line, they're reducing I, and reducing I means that they have to be increasing their angular velocity in order to keep the angular momentum fixed. So this is probably going to be embarrassing, but what can you do? Here I've got a slippery floor, and I'm going to start spinning with my arms and legs out, and then I'll bring them in towards my center line. So actually already quite dizzy because I never learned how to spin without getting dizzy. Probably should have thought about that before I did that. Great. But that is the principle of the conservation of angular momentum in action. It also means, just like our example of throwing a hat on an icy lake, suppose for some convoluted reason I was standing on a frictionless surface and I was trying to screw in a light bulb, right? So I'm imparting some angular momentum to the light bulb as I maybe spin it around, and that means I get an equal and opposite angular momentum myself. And so I will start spinning counter-rotating relative to how I was trying to screw in the light bulb. Okay, great. So we have these quantities, momentum and angular momentum, which are conserved. At the same time, we see velocities of objects changing all the time. So how is it that that process happens? How is momentum transferred or exchanged between objects? The physics term for this process are impulses. Now, the idea here is, just like on the frozen lake example, where you started out with zero momentum and you ended with zero momentum, but two objects moving in opposite directions, a similar thing happens all the time when objects have impulses and change their momentum. So if I'm just standing still and then I start walking, so I've gained velocity, and that means I've imparted a backwards momentum or a negative momentum back on the Earth. And the Earth's rotation actually does change a little bit, although the ratio of our masses is so disparate that we never measure or observe this kind of change in the velocity of the Earth due to us changing our velocities. So momentum is transferred by these impulses. And what is an impulse? An impulse is a force exerted on an object for a duration of time. So it's a force over some duration. Okay. So in physics, we often use this symbol, capital Greek letter delta, to mean a change in some quantity. So the change in, say, the linear momentum, delta p, is given by a force, vector f, multiplied by some time, right? So it's the product of a scalar times a vector. You can kind of contrast this with doing work, where work was a scalar quantity associated with doing some amount of force, exerting some amount of force over a displacement, over some vector distance, right? And so here we had a dot product of two vectors to give us a scalar, because work is a scalar quantity. But impulses are changes in momentum, and momenta is a vector quantity, and so I have not the dot product of two vectors, but just a scalar times a vector. So the change in momentum, this impulse, points in the direction of the force, and the magnitude of the change is given by how long you exert that force on that object. So just like in doing works, and remember when we talked about ramps, we could do a big force over a short distance to just lift something straight up, or we could do a small force over a long distance, doing exactly the same amount of work, but say pushing it up a ramp at some slope. Well, similarly, you can have changes in momenta, these impulses that come from doing small amounts of force over a long time, or big amounts of force over a very short time, right? And this kind of idea plays a big role in what happens during collisions between two objects, right? Because when two objects are colliding, they are exerting forces on each other over the duration of that collision. So the fact that the duration of a collision matters explains why, for instance, cars have bumpers in the first place. The bumper is like a soft, more flexible material that allows a collision between two cars to happen over a longer time. Even if it's still a fraction of a second, it's longer than if you had no bumpers and it was just like rigid steel and you just like almost instantaneously had cars colliding and bouncing off each other. So we'll learn a lot more about collisions in the next chapter, but you can kind of already have maybe a little bit of an intuition that if you're having the same change in your momentum as you collide off and bounce off something, but you have the option to either do it over a long time or a short time, if you collide over a very short time, but you have a fixed amount of momenta you're going to change, you're going to experience huge forces. But if you can kind of stretch that collision out over a longer duration, you will experience, or the object will experience, lower forces over this longer time, right? And so that's why cars have bumpers or crumple zones, for instance. You spread these incredibly violent collisions over a longer period of time so that the forces experienced are reduced. Actually, writing these impulses in this way together with thinking about Newton's third law, you can maybe start to understand why momentum is a conserved quantity. Remember, Newton's third law tells us that, objects exert equal magnitude but opposite direction forces on each other, right? And, if two objects are colliding over some time, over that whole duration, they'll be exerting equal and opposite forces on each other. And that means that any amount of momenta that one object gains, it must have been lost by the other object, or any amount of momenta that one thing has, gets transferred to the other, depending on the nature of the collision, as we'll see. Okay. So in the lecture notes, there's a question about thinking about both that idea and the idea of conservation of momentum, in the first place, to answer questions like, suppose you're going to throw either a beanbag or a rubber ball at your friend at the same velocity, and those two objects have maybe the same mass, which of those two objects will transfer more momentum to your friend, maybe making them more likely to fall over or whatever. Great. So, this is the equation for impulses associated with linear momentum. I suspect you can already guess the equation associated with impulses, changes in angular momentum, because again, our whole prescription, the way we've set up our language of rotations, lets us say, oh, something to do with momenta is equal to a time times a force. I just need to put the angular analogs of everything in there. So a change in some other type of momentum is equal to time times the version of force that's relevant for angular motion is torques, right? And remember that torques are like lever arms crossed with forces. So, again, our kind of canonical example was we had a seesaw, we had an object at some distance from the seesaw, maybe the force of gravity is pointing straight down, so there's our force, and there's this vector going from the pivot point to the location that the force is acting. So I guess I should have drawn this about there, and that's the lever arm. Great. Okay, so by thinking about these things, knowing that you get impulses of rotation when you have torques acting over time, and you have impulses of linear momentum when you have forces acting over a time, you can already start to kind of guess, well, what physical situations correspond to needing these different quantities, right? So for instance, first, suppose I have two blocks that are maybe moving at some constant velocity towards each other, along the line separating their centers of mass. Right? So they're going to run into each other when they both get to this point, and they're going to exert forces on each other. And you'll notice that those forces, if I think about these blocks being able to rotate about their centers of mass, the lever arm associated with, well, I'm going to have a force on this object, pointing in this direction, and the angle that it makes with the lever arm in this case is 0 degrees or 180 degrees, depending on how you're thinking about it. And remember that the magnitude of a torque is given by the magnitude of the lever arm times the magnitude of the force times the sine of the angle between them. So because the angle is 0, there's going to be no torque involved in this collision. And so that tells me already that this is going to be something that just involves conservation of linear momentum. On the other hand, if I set up my situation a little bit differently, I still have this block flying over here at some velocity. I'll call these V1 and V2. And this was meant to be a force from the collision. I still have this block going over here, but my second block maybe is over here. They're still going to collide, but there's just going to be like a glancing collision, near these corners of the blocks. And now you can see, well, I've got a force that's pointing this way, but the angle that it's making with this lever arm is no longer 0 degrees or 180 degrees, it's something in between. The lever arm is relevant, and these objects are going to start rotating. And, you've seen that if you've just thrown objects with glancing trajectories, that after they collide, both the way they translate changes and they both start rotating. Right? That's great. So that covers what we want to discuss about collisions for now. But like I said, we're going to do a lot more details in the next chapter when we learn about the differences between kind of elastic collisions and inelastic collisions. And we'll also encounter things like springs and roller coasters and fun mechanical motion of that sort.